Hi everyone, welcome to my YouTube channel, Zenith GATE Mechanical. So in the last video, I have discussed the three questions which came into the GATE 2025 mechanical paper from the manufacturing. So those who didn't watch that lecture, please go and see all the questions which I have covered. Now the next question is, this question came from the limit fit and tolerance. So what is the question? In assembly hole size is 30 plus 0.03, that is nothing but the upper limit of hole, and the shaft size is 30 plus 0.02 mm. So you have to identify this assembly belongs to which category. So it is a loose fit, or it is a clearance fit, or it is a transition fit, or it may be a interference fit. Now, first of all, you have to draw the zero line or the basic line for the hole and shaft size, which is nothing but the 30 only. Then you have to put the upper and the lower limit. Okay, so how you will solve this question? This question is straightforward. So let us suppose this is the zero line or the basic line. This is the zero line. That means I'm assuming this is nothing but a 30 mm size. So what will be the upper limit of hole? Upper limit of hole is 0.03. Lower limit is not given. So that means you have to assume as a 0.00 or 0 only. That means the lower limit of hole is this one, and the upper limit of hole is 0.03. So this is nothing but the tolerance for hole. So the upper limit of hole is nothing but 30.03, because the tolerance which is nothing but 0.03. Similarly, for shaft, 30 is the basic size and 0.02 is the upper limit. Okay, so let us suppose the 0.02 is nothing but here. So this is the tolerance for shaft, 0.02. So what will be the upper limit of shaft? That means it will be 30.02. 30.02. Now, if you see both the tolerance zone, that means this zone, tolerance zone for hole, and the tolerance zone for shaft, they are overlapping with each other. When this is the condition, when both the tolerances are overlapping, then it is called as a transition fit. Then it is called as a transition fit. So what is the correct answer for this question? The correct answer is option D only, transition fit. Why? Because the tolerance zone are overlapping with each other. Overlapping with each other. So it is a transition fit. It is a transition fit. It is a transition fit. Maybe in any particular question, they can ask you what will be the lower limit of hole, what will be the lower limit of shaft. So this is the lower limit of hole, which is 30. Lower limit of shaft is also 30. Upper limit of hole is 30.03. Upper limit of shaft is 30.02. So this is nothing but upper limit of shaft. Okay. But in this case question, you have to identify the assembly belongs to which kind of fit. So the correct answer for this question is transition fit. So the option D will be the correct. Option D will be the correct. Okay. So let's move to the next question. So question number 5, this question came from the casting chapter. Liquid metal is poured in a mold cavity of size 200 into 200 into 200 millimeter cube. That means it is a cube only. All the sides are equal. Cooling in a uniform in all the direction with no additive compensation for shrinkage. No additive compensation for shrinkage. Consider volumetric shrinkage is 7% and the solid shrinkage is 8% during the solidification. The length of cube H after cooling down to room temperature. Okay, that means you have a mold cavity of this one. So after the solidification, you have to calculate what will be the edge length of the cube. Initially, the cube having edge length is 200. That means this dimension is 200 and it is a cube. That means all the dimensions are 200 only. Now, what is happening? After the volumetric shrinkage, that means 7% shrinkage is happening. And then there is a solid shrinkage of 8%. Okay, so first of all, you will go step by step. When there is a volumetric shrinkage, 7%, what will be the edge length? So initial volume, let us suppose having an edge length is A naught. So volume will be A naught cube. That means 200 cube. So after first volumetric shrinkage, which is equal to 7%. So first of all, I will calculate what is the edge length of cube after the first solidification. That means first volumetric shrinkage. So the volumetric shrinkage, which is given as 7%. So what will be the edge length? So let us suppose A1 will be the edge length after first volumetric shrinkage. So volume will be A1 cube is equal to 0.93 times of original volume, which is nothing but A naught cube. Okay. So the A1 you can easily calculate 0.93 to the power of 1 by 3 into A naught. So this value, once you will calculate, you will get 195.22. Okay, so this is the edge length of cube after first solidification or first volumetric shrinkage. Again, there is a shrinkage, which is the solid shrinkage, nothing but 8%. Now, the next one is after second solid shrinkage. Let us suppose the edge length of cube, now it will become A2. So A2 cube is equal to 0.92. Why 0.92? Because 8% is shrinkage. So 0.92 times of 195.22 to the power of cube. Okay, that means the volume after the first volumetric shrinkage, which is nothing but 195.22 to the power of 3. So A2 you can easily calculate 0.92 to the power of 1 by 3 into 195.22. Then you will get the edge length of cube after the second shrinkage, which is nothing but 189.868 mm. That means the final answer for this question is A2, which is after the second solid shrinkage, 189.87 mm. Okay, because you have to round off to 2 decimal places. So this will be the correct answer. Okay, so now let's move to the next question. This question came from the metal cutting chapter. What is the question? The cylindrical workpiece has a diameter D is 60 mm and the length value is given as 400 mm. The cutting speed is 25 meter per minute. Feed value, which is given as 0.2 millimeter per revolution. Taylor constant, which is given as 75, and the exponent value is 0.25. Tool changing time is given. The labor cost and overhead cost is also given. Tool changing cost per piece you have to calculate. Okay, so first of all, let me write down whatever the data given in this question. So the cylindrical workpiece has the diameter is given as 60 mm. Length of workpiece is 400 mm. Cutting speed is 25 meter per minute. Okay, so the velocity which is given as meter per minute. Feed value is given as 0.2 millimeter per revolution. Tool changing time is given as 3 minutes. And the labor and overhead cost is given as 5 rupees per minute. So you have to calculate tool changing cost per piece. Okay, so how you will solve this question? First of all, you will calculate what will be the RPM value from the velocity formula. So what is the velocity? Velocity is equal to pi dn divided by 1000. So from here you can easily calculate the value of n, which is nothing but 1000 into v divided by pi into d. So 1000 velocity is 25 and the diameter of workpiece is given as, let me check, the diameter of workpiece is 60. Once you will solve, then you will get as 132.63 revolution per minute. Okay, so RPM value you have calculated. So can you calculate how much machining time is required per piece? So L by F into N, where L is the length of workpiece, which is 400, and the feed value is given at 0.2. Now, RPM value you have calculated. Now, if you multiply this F and N, which is nothing but this is millimeter per revolution, and this is the revolution per minute. So this revolution will cancel out. So you will get as a velocity is nothing but millimeter per minute. Okay, and the length is already given in millimeter. So you will get machining time is minute only. So 0.2, 132.63. Once you will solve, then you will get 15.08 minute. Now from the Taylor tool life equation, which is nothing but v t to the power of n is equal to c. So from here you can easily calculate the t value. So c by v raised to the power of 1 by n, where a Taylor tool life constant, which is given as, which is nothing but 75, and the exponent value is 0.25. So this is 75. Velocity is nothing but 25. This is 1 divided by 0.25. So you will get as a tool life is 81 minute. 81 minute. Okay, so the tool life is 81 minute. So the machining time for one piece is this. So can you calculate how many number of workpiece? Number of workpiece which you can produce before going to the fail of this particular tool. So 81 divided by 15.08, which is nothing but 5.37. Okay. Now the tool changing cost is also given. You can see here, tool changing cost is rupees 5 per minute and changing time is 3 minutes. So the total tool changing cost, which is nothing but 5 into 3, which is 15. Okay. Now the number of workpiece you are producing 5.371. So can you calculate tool changing cost per piece? Tool changing cost per piece is nothing but 15 divided by this value, which is number of workpiece, because you are calculating per piece only. So 5.37. Once you will solve, you will get as 2.792. Okay, so once you will read the question carefully, you have to round off to 2 decimal places. That means the correct answer for this question is 2.79. So the answer is 2.79. Okay, thank you so much.